Hi everyone, welcome to the first video in the second unit. This is the derivative and the tangent line problem. This is part 1. You can see the objectives listed there. These are the things that we're going to do, so let's get started. To begin, here's a review of several terms that we're going to be using here. Back in geometry, when we talked about a circle, you can see the circle here and the radius. We said that a line was tangent to a circle if it intersected the circle in one point. This point was called the point of tangency. So a tangent line, a definition, is a line touching a curve in only one spot. This is the calculus definition. Now a secant line, when we had a secant line in geometry, that was a line that intersected a circle in 2 points. So we are now graduating from geometry into calculus, and you can see over here at this curve that the secant line is a line that joins 2 points along a curve. You can see it's a line, so lines have slope. Okay, and then this one here, down here, is the tangent line. It intersects the curve in 1 point. And so just a couple of definitions. So the problem that led to the discovery of one of the main parts of calculus was this idea of finding the slope of a line tangent to a curve at a single point. Now we know from lines that in order to find the equation of a line you need 2 points. From 2 points you can find a slope and then you can write the equation for the line, but we only have 1 point. We only have 1 point. So it's impossible with 1 point to draw the equation of a single line. So here's the definition of the problem. We have a curve, there's the red curve, and when we have a line with a point of tangency to that curve. Okay, so that's the problem we're trying to find. So one thing that we can do to solve this problem, instead of writing the line that is tangent, that we saw on the previous screen through this point, instead let's go through that same point but go to another point on the curve, and that becomes the secant line, right? It's close. It's an approximation, right? It's really, really close. Well, we want to approximate the slope of the tangent line. And so in general, what we're going to do is we're going to apply the limit process to this. We're going to say, we pick this point, we found the slope of that line, and then we're going to move and we're going to pick this point and we're going to find the slope of that line. And we're going to continue doing that, and as this point approaches this tangent point, we're going to actually be able to approximate the slope of that line using 1 point. So remember Zeno's paradox. It gets close, 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 half the distance, half the distance, half the distance. But it doesn't actually reach that point. And so what we're doing is applying the limit process to this. Okay, so we're going to take this just a little bit further. All right, and so what we have here is we have this function, f of x. You can see it right here. And we've chosen 2 points on that graph. And then we drew the line, the black line that connected those 2 points together. That's the secant line. All right. So we have on this one, we don't have actual values here. We say this is the x coordinate, and then this is the y, f of x, at that point. So you can see the point here, x and f of x. And then here, for this point, we have x plus some value h. Right? We just add it. So this is x plus h. I'm going to write that down here. Down here is, x plus h. This from here to here is h. Okay, and we know right here, bing, 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 right here, this is f of x, right there, the y coordinate. Well, if we add this as this amount up here, right, this one would be f of x plus h, right? Because f of x, this is the x coordinate, and then this is x plus h, so here we have the 2 coordinates. So we have, what are the coordinates of the 2 points? Well, the 2 points are x and f of x. And we have x plus h, the second point, right? We add h to it. And then whatever the y-coordinate is for that point, f of x plus h. So what is the slope of the secant line? Well, the slope of the secant line is the y, remember the regular slope from Algebra 1, y2 minus y1 over x2 minus x1, right? X sub 1. Well, the second coordinate, we have f of x plus h minus f of x, those are my two y values, over the change in x. So we have the change in f of x over the change in x. Rise over run, right? Slope. Well, if you can see down here, this is the slope of the secant line, that we have x plus h minus x, so the x's cancel, and you're left with something called the difference quotient. The difference quotient. Some of you have heard of that before. X plus h minus f of x all over h. And this is the slope of the secant line. So here's a summary page for what we've done. We said here that this difference quotient is the slope of the secant line. But as we make that secant line, you remember this, we have some kind of curve, right? And then we have this secant line here and here. As we begin to move this point back towards the original point, right, we are actually taking the limit. The limit as h approaches 0 of the difference quotient is the slope of the tangent line. So just the regular slope formula over here is the slope of the secant line, but when you apply the limit, which I don't have that written here, but I need to write it, the limit as h approaches 0 of the difference quotient is the slope of the tangent line. Therefore, the slope of the tangent line is said to be the limit of the slope of the secant line. Now this screen is full of notation. That's really all it is. It's just a bunch of notation. So here's derivative notation. It says the derivative of f at x is given by this notation. And it means the limit, I'm giving you some different notation, all the way down, okay? The limit as h, we use this as h on the previous screen, delta x goes to 0 of f of x plus delta x minus f of x over delta x. Now remember, delta x is in the same place as h was. It's just that added piece that you add going from one point to the other on the secant line. Right, provided that the limit exists. For all x for which this limit exists, f prime, that's how you say that, f prime, f and that's a little 1, is a function of x. Here are some other notations used to denote the derivative of y. The derivative is the limit as h or delta x approaches 0 of the difference quotient. So here this f prime of x is the derivative, y prime is a derivative. This, I haven't seen this very often, but that's there. More often you see dy dx. I don't think I've ever used that one. I would say this, the f prime, y prime, and this are all used most often in this course. So here's a summary at the bottom. You see that dy dx is equal to the limit as delta x approaches 0 of the change in y over the change in x. And that's the same thing as the limit as delta x approaches 0 of the difference quotient. And all of this is equal to f prime. They all mean the same, f prime of x, the derivative. The derivative is the limit of the difference quotient. It is the slope of the tangent line. A derivative is equal to slope, if you'll start to think of it that way. All right, I think it's time for an example. So what we're going to do is we're going to find the slope of the tangent line to the graph at a point, and then I'm going to add to this example at the end, we're going to actually write the equation of the line tangent to the graph of 5 minus x squared at the point 3, negative 4. So the first thing we need is we need the definition we need a definition of the slope of the tangent line, the derivative, right? So the slope of the tangent line is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. All right? So what I'm going to do first is I'm going to find f. I already know what f of x is. That's what that is. I need f of x plus delta x. Okay? And so that's going to be 5 minus x plus delta x quantity squared. So I'm going to do a little simplifying. Okay? So I've got 5 minus x squared plus 2x delta x plus delta x squared. I'm just multiplying it out. And then I'm going to write down here, I'm going to have 5 minus x squared minus 2x delta x minus delta x squared. All right, so that's this part. I can show you this right here. We've just written that part. Now we need the minus, and then I'm going to do f of x. Well, f of x is 5 minus x squared, so I'm going to go ahead and distribute the negative. So that'll be negative 5 plus x squared. And all of this is over delta x. All right, now, I didn't say equal because if you'll notice, we've just written this part right here. Once I simplify this a bit, then I will apply the limit, and that will give me the slope of the tangent line. Okay, so on here, what you'll notice on this is called the difference quotient, remember. This difference quotient has some properties that happen every time. And for instance, anything that doesn't have a delta x in it will cancel. So that the only terms that you have left here are going to have delta x in them. So I want to factor out a delta x from the numerator, and that's going to leave negative 2x minus delta x over delta x. Well, this is a form of 1. So now I'm ready to apply the limit. So I say the limit as delta x approaches 0 of negative 2x minus delta x. Remember, we use direct substitution. So I'm going to put a 0 in for delta x, and this is going to equal negative 2x. So this is what's called the derivative. Now, I need to know what the slope is at that particular point, the point that was given, 3, negative 4. So 3 is the x-coordinate. So I'm going to say negative 2 times 3 equals negative 6, and this is the slope of the tangent line. Now, in order to write the equation of a line at a point, we are going to use point-slope form, and I'm going to use the point 3, negative 4, and I start like this. Y plus 4 equals the slope, negative 6, x minus 3. So we have not only the slope of the tangent line, we also now have an equation of the tangent line, and we have the derivative, which is the slope of the tangent line at that point. This is a long example. We're going to work a lot of these in class, but I think you can get the gist of it from this one. This is a very important summary and you need to write this down. You're going to hear this many, many more times, but this will be probably the first time you've heard it, so be sure and write this down. So for the summary, the derivative finds the slope of a curve at any point. The instantaneous rate of change means slope, guys, rate of change, the instantaneous, at an instant of time, at a point is also the derivative. Slope of the tangent line is the derivative. Now it's the instantaneous rate of change, means the same thing. If f is differentiable at x equals c, then f is continuous. It has to be continuous. Now, it doesn't have to be continuous to find a limit, but it does have to be continuous, right, to find, now I need to say that a little differently. There could be a hole in the graph, a removable discontinuity, and still have a limit. But a derivative can't exist there. A hole matters to the derivative because think about it, you need 2 points, right? Or you need a point. If the point doesn't exist, the derivative doesn't exist. So that's important. However, if f is continuous at x equals c, then it may or may not have a derivative. It may or may not be differentiable there. And we're going to learn later what that means in terms of what the graph looks like. So if it's differentiable, it's continuous. But if it's continuous, it might not be differentiable. Okay, so this is not a biconditional statement. This is just a straight if-then conditional. If it's differentiable, then it's continuous, because the opposite is not always true. All right, so I hope you got this. This is quite a lot to take in. But we're going to continue on with this subject in the next video and, of course, in class. And we're going to go over it and over it and over it until it becomes second nature, because the derivative is the second major point in calculus. In fact, most of calculus can be divided into differentiation and integration, and they work together. So be sure you get all of this information in your notes, and not just write it down, but go back over it, think about it. And also consult your book, because the book has a lot more examples in it. In fact, we're going to look through the book so you can kind of supplement some of your notes. So I will see you in class.